Late for July's after the training session that we had left me behind, and just didn't have a chance to get one in, but we'll get a couple in this month to get caught up on that. We're going to talk about network address translation today. First, a bit of project news. Our first training session was completed I guess a couple weeks ago now. It went well. We had a good crowd, and we got another one coming up soon here in September. This first couple sessions, those are in person here in Austin. You can get all the info at pfSense.org/university. We will be doing online ones at some point later this year if you don't want to travel. So keep an eye out for that. 2.1.5 release will be coming out before too long. Some security updates with OpenSSL again, and some other minor bug fixes and things along those lines. Probably see that within the next week or so. Nothing as significant as what Heartbleed was, but some things that you'll want to get patched. We now have the FW7551 available at store.pfSense.org. Good, another Rangeley Atom platform. A little lower than our 2758, but it's a nice new platform. Something to definitely check out. And for any hardware that's support bundled that you buy at store.pfSense.org this month, we'll throw in a free gold subscription. Granted, those of you here already have one, but that would just extend yours out another year. So network address translation is the modification of an IP packet header. Replacement of source and/or destination IP, or source and/or destination port for TCP or UDP. Common usage, internet access is the most common, but it can also be used for a variety of other things like connecting conflicting networks together, working around routing issues, and other things along those lines that we'll go over and show examples of. It's not a security mechanism. Some people think of it as providing some semblance of security, and it's not really designed for that. It's not security isn't really a result of how it functions or anything along those lines. And the whole point of NAT was to extend the lifetime of IPv4. So these are the things that NAT will potentially translate depending on how you have it configured. For any protocol, you'll have the source and destination IP that you can potentially change. And then for TCP and UDP traffic, you'll have the source and destination IP, but also the source and destination port. So here's an example of what a packet before NAT and then after NAT will look like. So this is just one of Google's IPs. You try to browse to http://google.com. Your internal machine, if its source address is this 172.17, it will source traffic from there. It'll pick a random source port. Just picked one out of the range at random, 23847. It might be anything between 1024 and 65535, depending on how your OS is configured. And then the destination port will be 80. And that's how it looks whenever it comes into LAN. Now, whenever it leaves WAN, it needs to have your public IP as the source, and it'll retain the same destination IP and port, but it will change both the source IP and the source port by default. So in this case, I just picked another one at random, and this is the WAN IP of our test and demo setup today. And that's how it would look after it gets translated. So first we'll go over outbound NAT. So outbound NAT is translation of the source IP and the source port. Optionally, both of those. It will be both of those by default, but you can configure it manually if you need to accommodate any needs that are different from the usual circumstances. Automatic outbound NAT is what's enabled by default, and that just NATs all of your internal subnets out to your WAN IP. Or if you have multiple WANs, then it'll NAT it to whichever WAN that the traffic is leaving. And then the manual outbound NAT is the other option, and that's where the outbound NAT rules are fully user configured. So in that case, you'll like if you have multiple public IPs, that's a scenario where you can control what gets NATed to what address. And we'll go over some of the rule configurations here. Is everybody hearing me? Someone said they didn't have any audio. Yeah, thanks, Jim. I mean, I thought my test system had the audio coming through as well. This is our test setup here. We have the default NAT in place at the moment. So the outbound NAT rules are defined under Firewall NAT and the outbound tab. So automatic is enabled by default, and that will, for the circumstances that we have here, if we go look at what our interfaces are. So we have a WAN interface, a LAN, a DMZ, and a WAN 2. So the way this is currently configured, any traffic that goes out of WAN will get NATed to this address, and any traffic that goes out of WAN 2 will get NATed to this address. Now, the system determines for automatic NAT whether or not to translate for an interface, whether or not it's an internet connection. So if you have a static IP connection, you have to have a gateway selected here for it to be treated as an internet connection. If there's not a gateway here, it assumes that it's an internal interface and not an internet connection. Any of the dynamic configuration types, those are automatically assumed to be internet connections for purposes of outbound NAT. So if we go out to a host that we have that's acting as an internet host in this case, we'll see what we're going out of the WAN IP, which is that address there. And then if we force it out of WAN 2 instead, and with browsers wanting to cache the content and cache the TCP connection, you got to refresh a number of times before it'll ever actually open a new connection to get the new path out the other WAN. And then we can see we're coming from the WAN 2 IP there. And we'll change this back to default. And I'll leave that WAN 2 one in there. That one will never match the way that it's configured right now, but then we can come back and just disable this first one, and that will get us out via the second WAN if we need to. Since the first match wins, this will match all traffic, and this will never get hit with the configuration as it stands at the moment. So go back to outbound NAT. Whenever you change from automatic to manual, and you have nothing defined down here in the list, it'll automatically generate the entire list of what outbound NAT rules that it was automatically putting in there for you. So that gives you a starting point if you need to manually configure all of your outbound NAT. And most of the time this is more verbose than it really has to be. We have here the source for the LAN network, and then we have a couple there for that, and then we have the source of the DMZ network, and then we have the same thing for WAN 2. These mappings apply to the interface where the traffic leaves, and we have a static port for 500. Get into the static port in a minute. We can trim this down pretty significantly most of the time. The source 127.0.0.0/8, that's for circumstances where you're binding squid to a local host, and that's what does the NAT in that circumstance. The port 500 for ISAKMP traffic, to not rewrite the source port on that. That's more of a legacy thing. Generally, VPNs use NAT-T, so they aren't even they don't care in that case whether or not you rewrite port 500. So most of the time, it's safe to get rid of that as well. So we've got it down to 2 rules, and so we deleted the DMZ subnet that's .2. So we'll need to change the source on these to include that network. And there's no harm in overmatching here. This just specifies what source will be translated if it actually leaves the WAN. So overmatching has no bearing on routing or connectivity or anything along those lines. And it can be easier to overmatch because then if you add a subnet in the future, then you don't have to remember to go back in and update accordingly. We'll do the /16 in this case. Could just as easily do the 172.16/12 to include the whole private IP space. And this is functionally more or less the same as the automatic outbound NAT that we started with in this case. Any traffic leaving WAN from any of those sources, 172.17.x.x, will be translated to the WAN address, and we'll rewrite the source port. And where you have multiple public IPs, you'll have the translation option here to pick a different address that it will translate on. And you also have a lot of flexibility if you want to specify something that doesn't get natted. You can do so by checking the box there. The interface is which interface the rule applies to, and that's as the traffic is leaving that interface. So it's WAN in this case, and for your just general internet connectivity purposes, it's WAN. And the protocol allows you to be more specific about how you translate things. So if you only want to translate one specific protocol one way for a certain reason, that allows you to do so. The source is the original source of the traffic. So that's your, for WAN NAT at least, that's your internal subnets. And the destination is generally any, because that essentially matches anything for the entire internet. If you needed it to only apply more specifically to a particular destination, or not one particular destination by using the not option here, you can specify that. And then this is the address that it gets translated to. The interface address option just automatically fills in whatever the IP is on the interface as specified in the box here. So interface address in this case is the WAN IP. If you have any additional public IPs added as virtual IPs, you'll also see those in the drop-down here. So if we change this to .3, the WAN address is .2, then everything on our LAN will go out via .3. The port allows you to define what the source port will be if you're going to force it to a specific thing. It's almost always something you just leave blank. And static port is an option to not rewrite the source port. So there are some limited circumstances where you'll want to do that. Most of the time, you don't want that. VoIP is one example where you may need that for it to function. A lot of times you need it to be disabled for it to function. So by default, unless something is not working, then just leaving it that way is the best option for it. Online gaming is another option that another service that frequently gets broken by rewriting the source port. And now anything that's going out of WAN will go via 2.3. And then we can see that the source is 2.3. So the server that we're hitting here is effectively the same as just a server out on the internet. It's seeing things the same way that an internet server would in a normal network circumstance. And then for the second WAN rule, you can do the same thing. You can change what the interface translation is. You just want to make sure that you always pick an IP that is actually associated with that internet connection. So if we try to use WAN 1's IPs on WAN 2, that would not work. Make sure we have to have an active connection up there. And then once you do establish a connection, if you go look in diagnostic states, in a real network, you'll have a lot more, so it'll be something you'll probably want to filter down. And that's the IP of the web server and then port 80. And then we can see here, the client that we're on is the 172.17.1.100, and it got translated to the 2.3 IP. The original source port, 38770, was rewritten to 30471, and then it was sent on to the web server in question. And that's the outbound state from the WAN side, and then here's the one from the LAN side, so where it just shows the original source IP and port, and the ultimate destination and port. So filtering in states is a good way to kind of confirm your outbound NAT configuration, see what it looks like, what things are getting translated to, and then seeing established there. It's working. And one of the circumstances that you may encounter is wanting to do static port for, let's say, a VoIP PBX. So if we had a VoIP PBX at, say, .200 on this network, you can the options here are either network or any. But if you need to specify a single address, a network /32 is just a single IP. And then we can leave the remainder of the translation at defaults, or if you have an extra WAN IP that you want to use for that system, you can choose it there. And then we'll check static port. And you want to make sure that that comes first. So the first matching rule wins for outbound NAT, similar to pretty much every other part of the system where you configure NAT or firewall rules. So if you had this rule down here, it would never actually do anything because this would match the .200 IP, and then it would get translated accordingly to that. So just make sure that they're in an order where the first matching rule does what you need it to do. And you can always change back to automatic outbound NAT if you switch over to manual and you find out that you get kind of stuck and you can't get connected to the internet and you can't figure out exactly what you're missing. You can switch back over, save, apply changes. You're right back to where you were originally. These rules have no impact on anything at that point. You can still modify them and change them and whatnot, and then if you change back to manual outbound NAT, then they'll apply. If you want it to regenerate the default rule set, if you've just gotten something messed up and you just want to start from scratch, you can delete everything that you have here. And then once you change back to manual, it'll automatically regenerate the default rule set there. And go back in the config history and revert the previous one. And 2.1 and 2.1x in previous versions, the only options are automatic or manual. Either the system takes care of everything for you, or you have to take care of everything yourself. In 2.2, we've got a new option to allow a hybrid mode. And I've got a 2.2 system to show that on. System. There we go. So there's two new options on the outbound tab in 2.2. It shows the automatic rules by default there, and it has new options for hybrid outbound NAT and disable outbound NAT. So in 2.1.4, if you want to completely disable outbound NAT, you can just set it to manual and delete all those rules. So if you have no mappings at all and you're on manual outbound NAT, that means you're not natting anything. That's the appropriate scenario if you're just using it as an internal router, or if you only are using it to route public IPs, so you don't actually have any private IPs anywhere. So the hybrid outbound NAT makes life a little easier. You don't have to, if you need just one little change to the outbound NAT behavior, you don't have to manually configure all of your outbound NAT. If you change it to hybrid, then it will use the mappings that you define, and then it will apply all the regular outbound NAT rules then from that. So in that case, if we just needed to do something like what we set up previously with like a PBX. And you can see that we're on automatic still. You can see that it's not applied because it's grayed out here. So it's just there to be defined and not actually being used at the moment. So now if we just change over to hybrid. And apply changes. So now we have the static port for PBX's IP, but then we also have the automatic rules that apply after that. And that's handy because in a lot of circumstances, you really only need to change one specific thing like that, and you don't really want to have to go back and manually maintain your outbound NAT rules for everything. And there's also an option here to disable outbound NAT, which is the same thing as just setting it to manual and deleting all the mappings. Just quicker to pick that, and more clear if you don't understand that that's how the system works there. And this just illustrates the network that we're working with here. We have the one client that's inside on the LAN, and then we have two WAN interfaces on this system, and their IPs are 2.2 and 100.2. So another use of outbound NAT is fixing any kind of broken return routing that may exist on your network. For instance, we have just a buggy device that I'll illustrate here. Sometimes you'll run into devices that just won't use their default gateway for whatever reason, and sometimes you'll encounter a device that it thinks its subnet is larger than what it really is configured to be, and it can't route for that reason. Uh, Most of the time in circumstances like this, there is an underlying problem that can be fixed. But sometimes with a certain buggy device of some sort, it's just not possible to fix it, and it's easier just to work around the issue by translating the source address. So I'm going to break the test system in the second network here. Okay. So we have this device here at 2.10. And if we bring up a terminal here and try to get to it, first we'll make sure we can get to the DMZ's interface IP. That hosts So we've tried to ping 2.10 and we just don't get anything. If we go over here to packet capture, let's filter on that IP and just see what it looks like. Okay, it's long enough it caught at least something. Okay, and the IP of the machine that we're on is the 1.100. And then there we see the ping leaving the DMZ interface going out to the 2.10 host. After that, we see something interesting. This host is doing an ARP lookup for the IP of this client. This client is on a separate network. It should never do an ARP lookup for that IP. And normally when you see that, it's because the host has a misconfigured subnet mask, and that's actually how I replicated this scenario here. I gave it a /16 mask instead of a /24. And then it thinks that all of 172.17xx is local to it. But this is also the exact behavior that some broken devices will exhibit. So in this case, it's a FreeBSD server. It's perfectly fixable just by putting the proper subnet mask on it. But we'll pretend this is just a broken device that is just unable to route back correctly to its default gateway. So after investigating it to a point that you're confident that that's the issue, it is configured properly, it has the right subnet mask on it, and it's just doing this broken behavior for whatever reason, you can work around that just by translating the source address to something that is local on that network. So we're still in manual outbound NAT here. And we'll add a new rule. For interface, we'll choose DMZ because we want to translate the traffic when it leaves the DMZ interface. We'll do any protocol. Source network, we'll just set to any in this case. We could set it to 172.17.10/24 to match only the LAN subnet. Probably best just to specify any for this circumstance. Destination, we just want that single host because we don't want to translate the source IP for everything on that network. We just want to do it for that one broken device. And then we'll just translate it to interface address. Okay, so anything leaving the DMZ, any source, going to 2.10, will get translated to the DMZ address. Go back to our ping, it's still sitting there. Remember, anytime that you change any NAT config, firewall rule config, anything else, any connections that are already established and already in the state table, those changes do not apply to that host. So we'll filter on that 2.10 IP. And there we see the ping, the inbound direction, outbound direction. And then if we just kill those off, now we see we're getting replies. And then we can see here what's happening. So the 1.100 sources the traffic. Then when it leaves the DMZ interface, it gets translated to the 2.1. That's the IP of that local interface. And then passed on to 2.10. So we just worked around the fact that that host does not have proper return routing information just by translating the source IP. So as far as this host is concerned, this is the only IP that is actually talking to it in this case. And we do have a web server running on there. So we can see that we're coming from 2.1 as far as the server can see, that is our address. So that's just the firewall's interface address there. Usually that's a problem that you can fix without actually doing this, but if you exhaust all other possibilities, then it's a good option. Okay, now going over one-to-one NAT. So one-to-one is a mapping of one internal to one external IP. So if the host is going outbound on that particular interface, then it gets translated to that, and then for any traffic that's coming in from the internet on that IP will get translated to the internal address. It can be used for entire subnets as well, but they have to be equal size and sequential on the inside and the outside. So for internet purposes, usually one-to-one NAT on an entire subnet is not something that's practical because even if you do have a block externally, usually your internal IPs are not sequential. So usually it's do a single address. Now it's a different circumstance if you're NATing between internal networks or something along those lines. It is on a per interface basis, and so for each WAN interface, you would need your own a one-to-one specific to that particular WAN. And optionally, you can limit it to certain destinations. So if we just go back here and put everything on automatic again. Now one-to-one will override the outbound NAT. So if you do have both configured, the one-to-one will take precedence. And we'll use the 2.4 external public IP. And 1.100 is the IP of this host that we're on currently. Okay, and then we refresh our internet test host, and we are going out of 2.4 now. And if we filter on that internal IP, then we'll see there's our traffic outbound, and it's getting translated to the 2.4 address. Now that's only going to apply for traffic that's related to the WAN interface. So then if I come in from the outside to the 2.4, oh, I have an allow all rule in on WAN. So if we go look at the states, leave that ping running. Close that out to get rid of some of the noise here. So my machine here is the 33.123. It's actually coming in on a private IP just by the nature of how the inside part of this network functions. And then we can see here where traffic comes in there. It's coming into the WAN interface. It's destined to the .4 IP. And then the ultimate destination after it hits the one-to-one translation is back to the 1.100 internally. And without firewall rules on WAN, nothing will actually pass through the one-to-one from the outside. And without rules on LAN, nothing will pass outbound. So the reason that we can get pings through is because we have this rule in place here. If we disable that, and then we kill that, yeah, pings, they aren't like a TCP connection where they have a definitive end of the connection. So you can either wait a number of seconds for the state to time out on its own, or just go delete it and it'll be gone then. And now if we try to ping, we're not going to get through. So we go back over here and look at the firewall logs. We see here our traffic sourced from this machine's IP, or the host machine, and then destined to this client machine's address here. So the NAT applies first, then the firewall rules after that. So if you wanted to specifically allow something through that one-to-one NAT, they need a firewall rule on WAN with the private destination. For instance, if we want to allow ping, allow ICMP echo request. If you want it to be from the entire internet, source any. Though be careful what you open to source any. If you can restrict the source IP, that's best for most purposes. And we'll put the 17.1.100 IP there. And we start getting replies right away. So block traffic doesn't have a state created, so there's not like a state that you have to go clear out if you go from blocking to passing traffic. And then we can add the same thing, or something similar at least, for the second LAN. So then when this machine leaves WAN 2, it will go to .4. And one thing to keep in mind with all types of NAT, it only defines how the traffic is translated when it goes in a certain direction. That has no impact on where the traffic will actually go. It just defines that translation. When it goes out WAN 2, it'll use that. So right now we'll still be going out of the first WAN. If we go back to our firewall rules, where we can tell it where that client should go, we disable the first one so it hits the second one there. And then hit refresh a whole bunch of times. And we're not getting outbound. Let's go look at the states and see what it looks like. Okay, we're getting send closed. So we're sending traffic initiated from this host, source port 38797. Destination is the 164.0.50. It gets translated to the 51.4. And one-to-one NAT will retain the original source IP. Source port. So send closed means we sent the send out and we got nothing in response. So for one-to-one NAT, usually whenever you do that, it means you're missing a virtual IP. And I'm guessing I stopped at 4. And that was, wait, what was that? Yeah, that is 4. I transposed 2 of the octets. That's a good example of where the state table can kind of help you determine what's happening there. And usually if you do end up in a circumstance like that, either you're missing a virtual IP or maybe you typoed one of the IPs somewhere like I did, or at times maybe it's because of an IP conflict or something like that, where maybe you're using the IP on another device previously, and that device is still plugged in, or maybe you just unplug that device and it's still stuck in the upstream ARP cache of your ISP, and you need to reboot your modem, or if you have fiber connectivity where the router's across the connection back in the CO, you may have to call your ISP to get them to clear that out. Okay. And the limiting it to certain destinations, and most of the time you just want to leave it to any, because whenever you have a one-to-one defined, usually you just want it to apply to all traffic in or out in those cases. But if you do have a situation where maybe you only want to translate it that way if it's destined to one particular remote network that needs to see it as a certain source IP or something along those lines, you can specify the destination there, and then it will only apply in that circumstance. And this just shows the example of what we were doing there, where we have the 2, 3, 4 on both of the WANs, and sending it out via different IPs on each. So now moving on to port forwards. So port forwards allow the rewriting of the destination IP and or the destination port. So outbound NAT is the source port and IP optionally. Port forward is the destination. So for an example, we'll forward port 80 inbound to one of the servers, and then 2222 as well, just to show a different port externally as internally. So in the case of port forwards, the interface is the interface that the traffic comes in on, whereas with outbound NAT, it's the interface where the traffic leaves. So for most port forwards, that'll be WAN, and we'll do protocol TCP. The source, if you want to restrict like what IPs can get through it, you can specify that, but most of the time you don't want that to be any, at least if you want it to be reachable from the entire internet. And then the target IP is the ultimate IP internally that it's going to end up at, which 1.10 is a server that we have on this network. And the no XML RPC sync is if you have a high availability pair, you can prevent it from syncing across to the backup if you need to do that for some reason. Usually it's not the case. Reflection we'll talk about in a bit separately. Filter rule association, you pretty much always want to use add associated filter rule. It just makes things a bit easier to deal with. Anything coming on the WAN address on 80 will be forwarded to that server. So if we go back to here. Okay. That is our WAN IP. And then the server 1 is the server that we're forwarding it into. And it sees our address correctly in a real world scenario. That would be a public IP coming in there. And if you want to add a port forward that's similar to one that you've already got there, the plus to the right, just like in Firewall rules and several other areas of the web interface, you can add a new entry based on the existing one. So it creates a new rule, and it pre-populates it with everything that's configured in the rule that you duplicated. So now we have the exact same rule that we just configured. Destination port range. So we want to pick up 2222 externally, and we want to send that to 22 internally. Anything coming into WAN, that's protocol TCP, any source, destined to the WAN address, port 2222, then gets translated to 1.10, port 22. So we'll apply that. And we'll go back to this machine. And telnetting to a port externally is a good way to test certain things. Anything that's running on TCP will answer in this fashion and give you some degree of output. Exactly what you get will depend on the service. So for SSH, you'll end up seeing something along these lines if it answers, and then if you hit enter a couple times, it'll kick you out with a protocol mismatch. Now these only apply to WAN, so if we actually want to forward on WAN 2 as well, we can duplicate again. And we'll change the interface to WAN 2. And when you change the interface, it automatically changes the destination from WAN address to WAN 2 address. So if you're just using the default pre-filled address placeholders there, it'll change that over for you. So really all we actually have to do in this case is just change WAN to WAN 2, since we're using that address there, and save it. And then we can do the exact same thing for the other one. Okay, so then we have the WAN 2 protocol TCP, any source destined to the WAN 2 address, port 80, gets redirected to 1.10 port 80. And then the same thing, destined to 2222, gets redirected to 1.10 port 22. Make sure I get the right IP. The habit of transposing that for some reason. 51100. We get it slow there. And if we go back to our browser, and that works as well. So now if we go back and check the states, we'll be able to see that translation there. That's at fin weight since it just dropped us out of it. But you can see that the original destination is that's the WAN 2 IP there, and the port 2222. And then it redirected it and sent it internally to the 1.10 port 22. Okay, so we have those port forwards working. We tested them from, this is effectively equivalent to an internet machine here. But what if we want to access those internally by their external IPs? So if we just try to go to 192.0.22, if we do that externally, we get the server. If we do that internally, we actually get redirected to HTTPS, and if we accept the certificate warning, we actually end up on the firewall. Now that's because if we go back and look at the port forward, this applies to traffic coming into WAN. It does not apply to traffic coming into LAN. So traffic coming into LAN does not match this, so it doesn't get redirected. It gets answered by the firewall itself. And since we have the HTTP to HTTPS redirect enabled, it just picks up that traffic, redirects to HTTPS, and you end up on the management of the firewall. Now, if you actually want to access those devices internally by their outside IP, that's where NAT reflection comes into play. So if you enter System Advanced and the Firewall NAT tab, And here you'll find the settings for reflection. So by default, it's disabled. It may or may not be something that you want to use. If you aren't sending a whole lot of traffic to be reflected back, it's fine. There are some caveats to how scalable it could possibly be, and depending on how many connections you're sending through it, you just may not want to loop that traffic through the firewall unnecessarily. You can use split DNS to resolve the host internally to its private IP, so you're not just sending traffic through and then translating it just for no reason. So if you need, there's two different modes. There's the NAT plus proxy mode and pure NAT. So pure NAT is the newer mode and the most preferred of the two. It's more scalable. It doesn't have quite the limitations that the NAT plus proxy mode does. There are potentially some unusual, rare circumstances where NAT plus proxy will be necessary or desirable, but virtually always you can get by with pure NAT. The NAT plus proxy is the only means of NAT reflection that existed in pre 2.0, I think. Yeah, I think all the 1x versions were the last ones, and this may have been introduced in one of the 2.0x releases or 2.1. I don't recall for sure off the top of my head. But this is the only mode that was available previously, so upgraded systems will end up on that. Just the behavior does not change. But if you're setting it up now, you pretty much always want to go with the pure NAT option. And if you're using NAT plus proxy, the timeout is relevant to that. If you want to do reflection on one-to-one, that's what the checkbox here is. And then enabling the outbound NAT options is necessary whenever you have a system that you're reflecting to that's on the same network. So we do have that circumstance, but we'll not check it initially, just to show you what ends up happening there. So we'll close out of that. And now if we go back to our WAN IP, of course the browser's really not going to be very happy. It caches that redirect from HTTP to HTTPS, so once you actually make that change, it can be difficult to get the system to actually initiate another connection to go back there, and it's still happening. Where did they hide the clear cache option? There we go. Okay, now if we try to browse there, we'll no longer get that old cache redirect. If we go back to the firewall here, we'll go look at the states and see what those look like. So we can see we have closed SYN sent as the state. So the SYN came through, was sent back to that internal host, but nothing actually ever replied back to it. So there's the initial request from this machine, the original destination, and the translated destination. And we'll just do a packet capture here for all port 80 traffic just to show what's happening here. So the request goes out, and the response is what is the issue in this case. So the issue is whenever this traffic goes out, back out into the LAN, back to the 1.10, it still has this original source address of 1.100 on it. So this host is expecting to communicate with this IP. But once it gets back to here, it still has this as the source address. This system sees that as local. It replies back direct to this system, and it breaks the TCP connection because it does not have the proper source address once it gets back to the client that's actually originating the connection. So if you have a circumstance where you're reflecting traffic back out to the same interface where that the client is on, then you have to rewrite the source address as well. So if the server was off on a separate network somewhere on let's say on the DMZ that we have on this system, and all the clients were on this LAN network here, then it wouldn't matter because the server would reply back to the firewall anyway, and then the firewall could retranslate it correctly so it would function. In this case, since they're on the same network, we have to have the source NAT option. So we'll check that. And we'll leave it on pure NAT. And save. And then anytime you're making changes along those lines with reflection or NAT or anything like that, it's best to delete the relevant states or just wipe the entire state table if you can take that that potential hit to the network. Just drop all your active connections. And now if we go back to here, close down the browser just to force it to get a new TCP connection going. Let's filter on that and see what it looks like. Okay, we still got closed and sent. we go direct there, we see that our IP is .100. And if we try to get there from the outside, we do have our correct address. And likewise for .2. I know what's happening there. We changed our LAN firewall rules to force all of our traffic out to the internet. So because this rule is matching, everything is forced to the WAN 2 gateway. It doesn't matter what's local, what's reflected, anything else. The whole point of policy routing is to override everything else that could potentially be there. So if we re-enable this rule here, it doesn't necessarily have to be this wide open. It could just be the destination of your WAN address if you do need all your other traffic to go out of WAN 2 for some reason. It could just be WAN net here. And I used up all the characters. Okay, go back in and kill all of our related states. We'll also kill our session to the web interface. There we go. And we need to just close out the browser and reopen it again. Let's see what our states look like. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. And also for the internal address of the server. There's the rule that allows that. Okay, got clean state table now. And there we go. So you see that the IP now is 17.1.1. So the reason it didn't work previously is because whenever it got back over, before we put the source net in, whenever it got back over to this server, it was sourced from 1.100, and then it would just reply direct back to this host, and it would end up with its own internal source IP rather than the external public. So reflection has to rewrite it back to this address. Otherwise, it doesn't match, and the TCP connection breaks. So this is what you end up with whenever you have reflection on the same network as the clients. Everything will come from the firewall's IP out of necessity. Otherwise, the connection cannot function because it has to be rewritten back to the original destination, and that's where it can be undesirable. At least if you make a lot of connections to that internal server. If you have some application or something that makes many requests to a web server or any other kind of server for that matter, looping those up through the firewall and back in and losing the original source IP, so it looks like everything is just coming from the firewall, can be very undesirable. In that case, you would probably not want to use reflection. You would use split DNS probably in that case, or the internal IP directly rather than the external. So that reflection is disabled by default. We went through the two different modes. Pure NAT always preferred, but NAT plus proxies are if you need it for some reason. And there is per rule control on each of your NAT configuration items. So by default, they use the global parameter. But if we go back in, we can look at the rules individually. So the system default will just use whatever we have configured under System Advanced. But if you want to override that for whatever reason, you can disable it or choose a specific means of reflection for this individual port forward only. And similarly for one-to-one, except the only option is enable or disable because there is no NAT plus proxy mode for one-to-one NAT. So this is a pure NAT regardless. And one other use of NAT is connecting networks that are conflicting. So you have a network like this. Let's say you have one LAN and you've had it on 192.168.1, and it's got all kinds of things that have hard-coded IPs or some other requirements where it's really difficult to change the network for some reason, and all of a sudden you need to bring up a VPN to LAN 2. And LAN 2 is also using 192.168.1.0. Yeah, so in that case, even if you do bring up a VPN, if you have this LAN 1 host here at 1.100 that's trying to talk to the LAN 2 host at 1.10, if you, say, kick off a ping from this LAN 1 host destined to 192.168.1.10, it's just going to issue an ARP request on the local network who has 192.168.1.10. If nothing exists with that IP locally, nothing will reply back and it'll just fail. If something else does have that IP on this LAN 1 over here, it'll reply back and it'll be pinging there. So it's impossible for this host to talk to 192.168.1.10 that's over here. So to work around that, you can NAT across the VPN so the opposite side always sees the network as a different subnet. So for this example, in particular, on this side we're translating between the local LAN, the 1.0/24, and just a subnet that we picked at random that's not in use anywhere else between these two different sites. So 172.16 1.0/24. So whenever it does a translation on a one-to-one basis between subnets like that, it just changes the first 3 octets of the address. So the real IP over here is still 192.168.1.10, but the translation is such that it shows up as a different address for the opposite side. of those sides. This side should actually be 16 because the translation happens over here. So this one knows that it's only knows of its local 192.168.1. So it sends out to the other end though that it's it can use that network there to reach it. So in that case, you would then use the 172.16.1 on one side and the 172.18.1 on the opposite side. And that's a new feature in 2.1 whenever you configure an IPsec tunnel. Just fill in enough so I can actually add a phase 2. So for local network, in 2.1x versions, you have not just the network option, but you also have a translation here. So just to make it more clear, if we have the circumstance where the local network, the real internal network, is 1.0, but the network that the other side is actually communicating with is, let's say, 172.18.1.0. And then if the remote network is telling us itself is the 16 address, then we would have that there. So normally you wouldn't have this field here at all. It would be a direct connection between this network and this network. But in this case, since this is the actual real network on both sides, that's not possible for them to communicate without actually translating it in between. So this part here just tells the system that whenever the traffic from 1.0/24 comes in for IPsec to pick it up, and once IPsec picks it up, then translate it accordingly to this network here, and then pass it on to this remote. And the same is true in the opposite direction as well. So if the traffic comes into, say, 18.1.10, then it will be translated to 192.168.1.10, and it will be passed in if the firewall rules on the IPsec tab permit it to be passed in. So the only thing that this end actually talks to the other side about over IPsec is this. As far as the remote end is concerned, this network does not exist. It never sees it. It doesn't know anything about it. It's only locally significant on this specific firewall that we're on. Okay. And then once you have that in place, you'll be able to do that type of translation across. So it can actually communicate even though the two subnets are exactly the same. Now it's generally speaking better to avoid that kind of circumstance if at all possible. There are certain protocols that just will not work across NAT, or that you'll create all kinds of complications. Like Microsoft file sharing is one. If you have an Active Directory environment that you're trying to integrate across both sides, it's just not going to work at all if you're trying to NAT across networks like that. But outside of those two cases, there's not a whole lot of other things that get broken by NAT. So you should probably be okay in most other scenarios, and that's best to avoid where you can. But this kind of workaround is doable and sometimes a requirement. So one other usage of port forwards is for traffic redirection. So we'll use one example of DNS. So let's say that you have a network of that's public or semi-public, and maybe it's a coffee shop or a hotel or something along those lines, and you want to make sure that everyone is using your DNS server to resolve DNS, but you may have clients that are statically configured for some other DNS server possibly, and you don't just want to break their systems. You just want to grab their DNS and redirect it back to your own server in this case. So we can use port forwards just to redirect traffic in this fashion, the same, or at least in a similar context to what we do for traffic that's coming in from the internet. So we'll add a new entry here. So the interface is the interface that the traffic comes in on, so that would be LAN in this case. And for DNS, you'll want TCP and UDP. Most protocols are either one or the other, and you don't really want to overmatch by picking both. But in the case of DNS, that's one of the more rare ones that does not actually have, or it actually uses both rather than just one or the other. So we'll take traffic coming into LAN, protocol TCP, UDP, destination port, destination IP is any, and destination port is 53, and we'll send that to 1.10 is our internal DNS server. So before we apply that, we'll just configure this host manually to use an outside DNS server. And we'll run that one more time there. And we can see that we are communicating with 8.8.8.8 Google directly to get the results of that query. But we have an internal host name that we want our internal clients to be able to resolve of www.example.lan. And we'll get an index domain back for that. That's DNS's equivalent of host name not found. And we'll see we got that back from Google as well. So back to our rule, we'll redirect LAN DNS to server 1. So that matches anything coming into LAN, TCP, or UDP, port 53, any source, any destination, and it redirects it back to 1.10. Now, we'll need one additional rule here because we are redirecting this on the same network that this server actually exists. Without not redirecting the server's own traffic, it will just loop its own DNS endlessly forever back to itself, and it'll just get into a huge loop of DNS traffic. So we can just duplicate this, and we will set not here, the no RDR option. And we'll specify the source. And we'll use any destination, and we can use DNS is fine, or it could be any protocol for that matter. And we'll also want to make sure this is in the correct order, because if that rule doesn't come first, then this other one will match. So that one does not redirect for traffic from that source, but then this one will redirect anything that doesn't match that one. And now if we go back, it just filter on :53, end up with all of the DNS-related traffic. So you can see here, this client initiated a DNS request to Google, but we sent it to our internal server. And the same thing applies here with Outbound NAT. So if we didn't actually have reflection enabled, we would need to manually configure Outbound NAT. And reflection is not actually directly related to what's happening here. It just so happens that because we have reflection enabled and we have port forwards to that host, it's already doing the appropriate source IP translation. If it weren't, we would need to rule on LAN. We can just specify DNS only in this case. Okay, and that's the only rule that we have on LAN, so it doesn't matter what order it comes in. It's the only one that will match. So source of any 172.17 IP, destination of any 172.17 IP, and destination port of 53. So that traffic then will get translated to the LAN address. So that's it's for the same reason that we discussed before with why reflection has to change the source IP, because that device has to reply back up to the firewall, which then rewrites it back to, in this case, Google's 8.8.8.8. So when it gets back to the original client, it's sourced from the IP that it expects it to be. So this machine that we're on here now thinks it's talking to Google for that, but actually we're intercepting that and sending it to our internal server here. And now we get the name resolution for our www.example.lan. So DNS is one thing that's semi-common to redirect in that fashion. SMTP is another thing that some people do in similar kinds of networks and circumstances where you're providing internet access to the public at large generally. And in the case of SMTP, you're probably doing that because you want to scan your outbound email for any signs of a spam bot or something along those lines. So you don't let them send email out directly via port 25, but you intercept it, send it off to another server that then analyzes it so to an extent that you're comfortable that it's not spam, and then sends it on out to the internet itself. And in any of these circumstances, important to remember to negate your redirection for the host that actually has to get out on that particular service. Otherwise, you'll just end up with nothing functioning if you're looping that host's own, in this case DNS, traffic right back to itself. Any could melt down parts of your network as well, because it will loop very, very quickly around. It'll go up to the firewall, back to the internal server, and make a big circle and generate a lot of traffic possibly in the process. Okay. Anybody got any questions? Oh yeah, I see. Bill, you mentioned you got your audio working. You had to download the app. Yeah, the web client only lets you see the screen. For some reason, it doesn't actually um, have any kind of audio there. You do have to download the full app for it to have audio. V6 NAT. V6 and NAT is not something that should be done generally. And wow, providers really, really, really shouldn't tell you that you should be doing NAT in that case. Chase mentioned that Comcast suggested using IPv6 NAT, and we do have network prefix translation for IPv6, and that is the fourth tab in under Firewall NAT there. But that's not the only time you want to use this is when you absolutely have no other option whatsoever. So the circumstance where this is most common is smaller networks that are multi-home, to see if you have multiple ISPs, and you aren't big enough to get your own direct IP assignment and deal with the BGP and all that good stuff. Then you're going to have to send out one prefix for each internet connection. So your internal network in that case would use one particular prefix from one of the ISPs, and then if you're sending traffic out via another ISP, then you would translate it, replace the prefix with that other ISP's prefix. There is not a many to one NAT in IPv6 in what PF allows today, at least, and what virtually every firewall product allows today. There can be circumstances like that broken return routing scenario that we went through that are also a potential issue in v6 that would be helpful. So I think it's something that we're going to have eventually, but it's a horrible, horrible, horrible thing to use for general internet purposes. And the fact that Comcast suggested it is kind of disconcerting. I'm guessing that their head of IPv6 guy, shoot, his name escapes me at the moment, but he's very active in various communities to do with IPv6 and standards and CPE equipment, and actually we've had some exchanges with him about pfSense and IPv6 and making sure it works with Comcast. So, okay, it was Comcast level 1 that said that, not the IPv6 engineering team. So, yeah, we know the head of IPv6 at Comcast, and that is definitely not something he would ever recommend. So, if the level 1 support people haven't gotten the memo, that's, well, probably not surprising. It's Comcast; they can't seem to keep anything straight. But at least at the higher levels of engineering, they really know what they're doing. That's not something that I would see them recommending. Question: if you do get a delegated v6 with the prefix, how do you ensure devices are randomly rotated for v6 addresses to avoid profiling? The clients do that on their own. Actually, the IPv6 privacy addressing, they will just reassign their addresses on a periodic basis. But even having static IPs, I don't know that that's that much of a concern, really. Uh, I mean, a lot of my stuff is statically addressed on V6 or and V4. It's not really that. I guess it depends on what you're doing and what your concern is. Right. Yeah. So you would give up on NAT after moving well with IPv6, and but NAT does not actually keep your network private any more than anything else. So I mean, you're still identifying an address whenever you go out to the internet, and that's just a fact of life. They have to, whatever you're communicating with has to know how to get back to you. So you have an address in that case. Uh, whether or not it matters that somebody knows what that address is, I mean, I guess it depends on how secure that your devices are and what kind of filtering that you put in place on the WAN side. And that in and of itself doesn't so much keep your network private as you're still identifying what address that you're coming from. It doesn't tell the internal IP that's directly assigned to the machine, but generally speaking, that doesn't matter that much, I guess. It's kind of a hard change for people to get their heads wrapped around because a lot of people now, probably the vast majority, have grown up in this world where NAT's the standard, and that's that provides something that people are thinking of as some kind of privacy or security or something along those lines, and it's just really not the case. How do you pronounce my last name? Spiegler. It's German, or at least that's the Americanized pronunciation of the German. Proper German speakers would say it very slightly differently than that, but that's yep, Spiegler. Yeah, I do have the recording going. I'll stop it as soon as we're finished here and let it do its transcoding thing, and it takes at least as long as the meeting's duration to encode it. So it'll be uh, a few hours later by the time I get it uploaded. But yeah, by the end of the day, it will have it up in the members area. If you go to portal.pfSense.org/members, you can once you log in there, it'll be available for you. Any other questions? Okay, I'll shut it down for this session, and we'll see you guys here probably in a couple of weeks or so for the uh, August session. We'll send out an email to everybody to let you know since the dates and everything are all finalized. Thanks for joining.